Okay, so let's go through these quiz questions together. This was what you would have done after yesterday's lecture and what you're going to do after today's lecture for today's material. We just didn't require it last time. So after every lecture, starting with today, you're going to do one of these quizzes by midnight. And the link will appear on the course website shortly after the lecture's over. So here's the first question. True or false? If f is a convex function, then a valid constraint in a convex optimization problem is f of x equals 0. True or false? How many people think it's false? Okay, good. That's correct, because remember, equality constraints in convex problems, they have to be affine. It has to be like aj transpose x plus bj equals 0. Let's hold off on discussing why that is in a second. Like, why do we actually require that it's affine? You just remember that that's what we said in class. So, okay, false, you get a point for it. If you click true, it says, uh-oh, you didn't do it right. And then if you click false again, you get the point. I think actually, because I already did this quiz, that my scores are kind of fixed. But had you done what I did, which is suppose you click true first and then false, you'd get half of a point for that question. Okay, so the very worst you can get, if you're willing to brute force the quiz, is 4 out of 8. Because you get half credit for every question. Second question. Basically, all algorithms for convex optimization perform the same across all problem instances. Picking an algorithm for a particular problem is mostly a matter of taste. Okay, so had you been in lecture, hopefully we got that point across that, yes, the algorithms perform differently in different situations. Convex sets. Multiple choice. A set is convex if for every pair of points x, y, their convex combination is also contained in C. Formally, this means that tx plus 1 minus ty is in C for all t in R. Tx plus 1 minus ty is in C for all t between 0 and 1. Or tx plus ty is in C for all t between 0 and 1. Which one do you guys think? B. So why is A not true? It's because... Right, so t is not restricted here. So actually, this is the line segment not joining x and y, but passing through x and y. So it's not a segment. It's the line passing through x and y. So what kind of sets have this property? Affine sets, right? So these are like linear subspaces plus a shift. So a convex set, not going to have that property. This was the definition that we had in class. Okay, so, okay. Convex functions. A convex function must be defined on all of Rn. True or false? False, because convex functions, remember we said one of the conditions for convexity is that it had a convex domain. So Rn itself is a convex set. Of course, all of Rn is convex, right, if you follow the definition. But we also said that the function can have a domain which is not all of Rn, like log, for example. Or let's say minus log is a convex function. Log is concave, minus log is convex. But minus log is only defined on the positive reals. Okay, so as long as the function's domain is convex, that's OK. So this is not true. Fuse lasso. Fuse lasso loss term encourages the coefficients to match the observed data. True, right? I guess, that one's just kind of obvious by looking at the squared error loss. It was sum of, say yi minus theta I squared, where yi was the data and theta I were the parameters we're fitting. Fuse lasso penalty. The penalty terms in the fuse lasso problem encourage each coefficient to equal nearby values, each coefficient to equal the average of nearby values, each coefficient to equal 0, or each coefficient to line a line segment through 0. What do you guys think? A, right. I mean, this was a bit vague, but in both the 2D and the 1D cases, right, we had some definition of like an ordering, right, and or in the 2D case it was proximity, and we're penalizing differences across things that were adjacent. So this is what we meant by nearby values. Local optimality. In a convex optimization problem, any local minimizer is automatically globally optimal. What do you guys think? True or false? True. Yeah, that was the thing we proved at the end. That's kind of like the key property of a convex problem. And last question was feasibility. For point x to be considered feasible with respect to a given convex optimization problem, which of the following need not be true about x? X is in D, where D is the intersection of all the domains that define the optimization problem. X minimizes the objective, or x satisfies the constraints of the optimization problem. B, right? So of course, feasible doesn't mean optimal, right? So we don't need the point to minimize the objective, just that it's in the domain and that it satisfies the constraints. Okay, so that was it. That was the quiz. I think at worst it would take you twice as long as that, but hopefully you guys won't forget to do them. We'll probably remind you the first few iterations. Like we'll send an announcement out on Piazza saying the quiz is due at midnight, but then we're going to stop doing that pretty soon. So there's just a quiz after every lecture of that form. Any questions about that? See that we kind of use aspects of these subjects freely here when we talk about convex sets and functions. So just to recap what we did last time, this is a kind of a habit. I'll always recap what we did last time, although from now, for this particular lecture, since we went through the quiz, I guess it's not quite as important. But last time we talked about motivation for studying convex problems, simply put, because we can broadly solve them and understand them. And this was what a convex problem looked like, minimizing some function subject to inequality and equality constraints, where we required these inequality functions and the criterion to be convex, and we required these equality constraint functions to be affine. So hj had to be an affine function for each j. And the key property was any local minimizer. So anytime I minimize this criterion locally, which means that in a ball around a point x, right, of a certain radius, my point x looks better in terms of its criterion value than everything else. If that's the case, then that implies for convex problems that x is globally optimal. So it has at least as good criterion value as everything else that's feasible. We actually proved that last time. Okay. So here's an outline for today. We're going to talk about convex sets. We're going to go through some key examples of convex sets, some key properties, and then some operations that preserve convexity for sets. And then we'll do the exact same thing for convex functions. We'll try to take a break in between. So I think I have decent number of slides, and in past lectures I've spent a lot of time on convex sets, and then we've kind of been rushed for convex functions. I'm going to try to go through the convex set stuff somewhat quickly. I think that they're very related, as I expressed last time. Convex sets and convex functions, there's really kind of underlying themes for both of them. So if you understand one really well, the other will follow. So just to remind you, a convex set is a set with the property that if I have any 2 points in the set, the line segment joining those 2 points must also lie in the set. Okay, that's that amount there. It includes cases like this where I have a line segment between 2 points, and then a line segment leaves the set at some point. So this is not a convex set. Let's introduce some terminology. A convex combination of points. So if you give me any number of points, here I have x1 through xk. A convex combination is any linear combination of this form. So where I have weights theta i. So this is the sum of theta I xi. But these weights have a special property. They're all non-negative and they sum to 1. Okay, that's what we mean by a convex combination. Okay, linear combination is just one of this form in which these weights theta I are unconstrained. But this is what we mean by a convex combination. Okay, so a convex combination of 2 points is exactly that up there. It's tx plus 1 minus ty as t varies. Okay, those are all the convex combinations you get of 2 points. So and the set of all convex combinations of 2 points is just the line segment join those 2 points. Okay, in general, the convex hull of a set. So if you give me a set C, it doesn't have to be convex. Its convex hull, which we denote by conv of C, is the set of all convex combinations of its elements. So I pick any number of elements from the set C, I take a convex combination, and that thing is in this set. The convex hull of C. Okay, that's the way we define the convex hull. Another definition that's equivalent is that it's the intersection of all convex sets that contain C. So it's the smallest convex set containing C. It's another way to think about it. Okay, this is where I wish I had this thing working. Maybe I'll just use the blackboard. Do we know if they're...
He's coming right now.
He's coming right now. Okay. In that case, I will not use the blackboard. I'll just do this real quick. So for this bean-shaped set, okay, this guy we had, the convex hull is the set of all convex combinations of elements. So I can think about it in two ways. Pick any 2 points and then include the line segment in between all of those 2 points. Okay, so that's one way to think about it. So I'm going to basically be including all of this region as a result, right? Another way to think about it is that I'm looking for the smallest, right, the smallest convex set that contains this. So think about taking a bunch of convex sets. The smallest one is probably this guy. Another way to think of the, right, it's all of this. Another way to think about the convex hull. Okay. So I'm not going to be super careful in this lecture with closedness of a set and the convex hull. But on your first homework, you'll have some kind of interesting exercises to work through that emphasize that actually closed is quite an important property when it comes to discussing convex hulls. So, okay, just to remind you in case you've forgotten, a set is closed. That means that it contains all of its limit points. So if I take any sequence of points in that set, what that converges to is going to also lie in the set. Okay, that's one definition of a set being closed. Another definition is that its complement is open. So if all these, these terms are kind of rusty or confusing, take a look at some of the supplementary materials that we have on the course website. Turns out that actually closed and convex hulls, that's an important combination. So you'll do some exercises on the first homework that emphasizes that. So what are some examples of convex sets? And by the way, just to emphasize, this guy is always convex. Even if C was not convex originally, the convex hull of a set is always convex, right? Just by construction. So what are some examples of convex sets? There are some trivial examples, like the empty set is convex. Okay, we require this property to hold for every 2 points in the set C. If C is empty, it doesn't have any 2 points. So of course, that property kind of trivially holds. A point is convex. Okay, if there's just one point in the set, if the set's a singleton, then you'll see that definition holds. A line is also convex. Okay, a line segment is also convex. All of Rn is convex. These are all kind of trivial examples of convex sets. Here are some more interesting examples. Norm ball is always convex. So if you have any norm, let's say on Rn, which we'll just note by these double brackets here. So the L2 norm is one example. The L1 norm is another example. Okay, but if you just have any norm on Rn, then the set of all x for which that norm is less than or equal to R, that's a ball around 0 in a particular norm, that's a convex set. Okay, so I'll leave you guys to check that. That just follows from the fact that norms satisfy the triangle inequality. And they have this property called positive homogeneity, which means that the norm of like a positive number times x is that number times the norm of x. Okay, so those two properties together will show you that this norm ball is convex. And if you think about just the L2 ball, right, that is definitely a convex set. Think about it intuitively. Some other examples, a hyperplane is a convex set. So this is the set of all x for which a single linear equation holds. So A transpose x is equal to B. Okay, you can also check directly from the definition this one is convex. A half space is convex. This is everything that lies basically on a hyperplane and to one side. So it's the set of all x that satisfy a single linear inequality, right? A transpose x is less than or equal to B. Here A and B are fixed. A is a vector, B is a number, but they're just fixed, right? The set is defined in terms of x. And lastly, an affine space is convex. So we can think of an affine space in a couple of ways. Here's one definition of an affine space. It's the set of all solutions to a linear system of equations. A matrix A times x is equal to B for a given matrix and a given vector. Okay, those things are all convex. You can check directly from the definition that they satisfy. That's sufficient condition for convexity. Interrupt me if you guys have questions. I'll just kind of keep plowing along. So a polyhedron is an interesting object. We're going to see them, we'll see them throughout the semester. Polyhedra are just the set of all x that satisfy a bunch of linear inequalities. So remember, we defined an affine space by the set of all x for which ax is equal to b for a given matrix A, a given vector b. A polyhedron is the set of all x for which a times x is less than or equal to b. Hey, it works. Thank you to the mysterious people at MediaTek. Great. So what do we mean by that? This is a little bit unorthodox notation. Where's my pen? Here it is. ax is a vector, right, and b is a vector. So by ax less than or equal to b, I mean that every element of ax is less than or equal to every element of b. Okay, we're going to use that notation in general throughout the semester. If I have a vector, x and y, and I say x is less than or equal to y, we mean that xi is less than or equal to yi for all components I. Okay, that's the notation that we're going to use. Okay, so by this thing, ax less than or equal to b, the set of all x for which this is true, this is a polyhedron, right? We can also write that as the set of all x for which ai transpose x is less than or equal to bi, where this is the ith row of A for all I. Okay? That's another way to write it. So I have a bunch of linear inequalities, one for every row of A, and a polyhedron is just essentially the set of all x that satisfy all of them. So you can think of it as an intersection of half spaces, right? This is one half space for one I. If I require this to hold for, let's say, 10 i's, if I have a matrix with 10 rows, then it's an intersection of 10 half spaces. So that's one way to think about it. That's a drawing there. Note that the set of all x for which ax is less than or equal to b and also a bunch of linear equality constraints hold, cx equal to d is also polyhedron. So why is that true? Why can I, if this is my definition of a polyhedron, why is this also allowed? Okay, it's convex, but I'm actually claiming it's still a polyhedron. That's true. I mean, depends on C, but yeah, that's true. So, but still, why can I think of it as a polyhedron per the definition? This would be a trick that we use a few times in the class, yeah? Right, exactly. So I can always write Cx equals d as Cx is less than or equal to d, and Cx is bigger than or equal to d, right? And this guy I can always write as minus Cx is less than or equal to minus d. So there you go, right? I have these inequality constraints and these inequality constraints, and that make up, those are basically equivalents to requiring that Cx is equal to d. So I'm just going to add more inequality constraints. Okay, so simplices are a special case of polyhedra. A simplex is given by, you can think about it as given by, it's the convex combination of k plus 1 points. It's a simplex of order k. It turns out that it's not always possible, right, polyhedra are very interesting. I think we could give many lectures on polyhedra, but I'll try just to kind of give the basics. A simplex is a special case of a polyhedron of this form, where these points are affinely independent. So linear independence is something you guys should all know, right? If x1 through xk are linearly independent, that means that I cannot find, let's say, weights a1 through ak such that this linear combination is 0, but all the a's are not 0. Okay, so this being true implies that all the a's are 0. That's what linear independence means. Affine independence we can define in various ways. One way to define affine independence is actually as follows. I think it's probably the easiest to remember. These are affinely independent. That means that x1 minus x0, these k points are linearly independent. Okay, so think of x0 as some offset, and if I say that x0 through xk are affinely independent, that means that actually, once I get rid of that offset, that all those differences are linearly independent. All these vectors are linearly independent. Okay, so that's what a simplex is, and the most kind of common example of a simplex is the probability simplex. And it's just given by the convex hull of the basis vectors, the standard basis vectors in Rn. So it's called the probability simplex because it's just a set of all vectors W that are non-negative in every component. So remember, from now on, I won't even remind you necessarily. If this is a vector, then we mean that this inequality holds for each component. So W is bigger than or equal to 0 in each component. And also, by this I mean the vector of all ones. So this means the sum of the W's is equal to 1. So those are all, you can think of each of these vectors W as a probability distribution over the numbers 1 through n, right? Because they're all non-negative and they sum to 1. Probability simplex. Okay. How about some other sets? So cones are interesting and they're important. We'll talk about conic programming later in the course. Turns out cones are very general objects. A cone is a set that has the following property. If I have a point x and it's in C, then actually Tx is in C for all t that are non-negative. That's what defines a cone. A convex cone is what it sounds like. It's a cone that's also convex. Okay, so you can check that this property up here, that all positive multiples of a point being in the set, along with convexity, actually can be reduced to this condition, which is if I have any 2 points, x1 and x2 in C, then if I take t1 times x1 plus t2 times x2, for any non-negative t1 and t2, that must also lie in C. Okay, this is what it means for something to be a convex cone, this property here. Okay, so here's an example of what that looks like pictorially. If I have points x1 and x2, this is all linear combinations of x1 and x2 with non-negative weights. That's this gray area, extending out this way. Okay, so that's a cone containing x1 and x2. Is every cone convex? Why did we define a convex cone? Can somebody give me an example of a cone that's not convex? Yeah, that's a fine example. So here is it's a cone. Okay, these lines are supposed to be extending out, towards infinity. It has the property that if you take any point here, right? Suppose this is 0. So suppose I have a point x that's in the set. If I take any let's say positive multiple of x, that just takes me out this direction. It's definitely contained in the set. But that's pretty far from convex, right? It's like farthest from convex you can get almost. So cones are convex. Cones can be very spiky in some sense, but convex cones have a lot of nice properties, so that we'll focus on them. A conic combination of points is, I guess now that we define convex combination, this you can maybe think of as analogously, but it's for cones. So we just take any linear combination of points where all these weights are non-negative. That's what a conic combination is. And just to remind you, a convex combination is that plus the property that these weights must sum to 1. Okay, so a conic combination includes more weights as a possibility. And the conic hull of a set is the set of all conic combinations of elements of the set. Okay, just like the convex hull is analogously. So what are some examples of convex cones? The norm cone is a nice example of a convex cone. So it's the set of all x where x is a vector and t where t is a positive real, such that the norm of x is less than or equal to t for a particular norm. Okay, you can check that thing is actually a convex cone according to the definition. So let's actually draw what this looks like for the L2 norm. So this is called, if we look at this set, the set of all x, t, such that the L2 norm of x is less than or equal to t. If we look at this set, this is a convex cone because I just told you that all norm cones are convex cones. This is actually called the second order cone, the special name. It's also called the Lorentz cone, and it's also called the ice cream cone. There's some names for it. And let's just draw it where x is two-dimensional. See if my skills will suffice here. So when t is 0, the only point in this convex cone is 0, right? It's the only point that satisfies this when t is 0. As t gets bigger, and basically allowing more, like bigger and bigger concentric circles, So this is what this convex cone looks like. Okay, so it's all of this thing, what I'm drawing, extending out from 0. Okay, so it's everything that's in here. That's the second order cone, where x is in 2 dimensions and t is, as it always is, it's just 1-dimensional. Okay, so norm cones are really important. We'll see them a bunch. Similar name, but very different definition is the normal cone. It's also very important. We're going to see this when we talk about subgradients. We'll see it again when we talk about constraints and the KKT conditions. So if you give me any set C and any point that's in the set C, we can define the normal cone. And we say it in words, it's the normal to the set C at the point x. Okay, so it's the normal cone to the set C, it's the subscript at the point x. And it's the set of all vectors G that if you were to take the inner product of G with every vector in the set C, it's biggest at x. Okay, so you cannot find any other vector in the set C, y, that makes that inner product bigger than it is at x. Okay, so here I've drawn a picture of the normal cone at a bunch of different spots. So let's suppose this set is the set C. Probably it's easier just to draw it again. Let's suppose I have some set C like this. Okay, and let's pick a point let's pick a point here, for example. Okay, so let's suppose that this is 0. This is my set C, and this is my point x. So the normal cone is a set of all vectors whose inner product with x is biggest relative to all other points in the set. Let me change where 0 is to make this a little bit more generic. Suppose 0 is down here. Okay, so what vectors have the property that if I take the inner product of that vector with x, it's biggest? Right. It should leave perpendicular, in a sense, to the boundary from C. So actually the normal cone, just to be clear, I'm showing a translation of the normal cone. What I'm drawing as a normal cone is actually x plus the normal cone. Okay, but I'm just drawing that for clarity. The normal cone is actually this set. All these vectors. Okay, so all these vectors have inner product with x that's as big as possible. I think about the inner product of every vector in the set C. But I think when I think of the normal cone, it's easiest to draw it as leaving from the point in question. So it's really a translation of the normal cone. Right? A cone always contains 0. It has to always contain 0 by definition. Right? Because I can multiply by any non-negative number and stay in the set. So 0 has to be in the set. So this itself can't be a cone. That's actually the cone. This is just a translation of the cone. So I can define basically the normal cone anywhere. Another interesting point to define it may be here. So as I've drawn in the picture, you can check maybe your intuition to make sure that this case checks out. You can also check the definition. The normal cone is actually, in a sense, 2-dimensional here, not 1-dimensional. Okay, it's every vector that's in the conic, these two vectors. Because actually any vector here is going to have maximal inner product with this point versus everywhere else in the set. Okay, so that's the normal cone. One really interesting property of the normal cone is that it's always a convex cone. So this thing is always convex, regardless of the set C. Okay, so it doesn't matter whether C was this set or this set. Something very non-convex. The normal cone at any point is always going to be a convex cone. Let's check that. I've kept saying to you, you can check the definition for a bunch of different sets. Let's just do it for one set. Let's check that for this set just to be concrete. So it's a set of all vectors G such that G transpose X is bigger than or equal to G transpose Y for all Y in the set C. So how would I check that this is a convex cone? Well, I'll just go back to the definition, right? So let's suppose that X, I shouldn't use X. Let's suppose that G1 is in the normal cone, and G2 is also in the normal cone. Okay, and now it's up to us to check that all conic combinations of G1 and G2 are also in the normal cone, right? I want to check that T1 G1 plus T2 G2 is in the normal cone. Okay, but that's quite easy to do because I just take, let's suppose I take an arbitrary y and I compare the inner product of this vector with x to the inner product of this vector with y. So first I can just write this as, I can just expand out and say that that's this, right? Inner product is a linear operator. And just take the inner product of G1 with x, G2 with x, and then multiply by T1 and T2 and carry that through. And okay, so now actually I know that this is true. I shouldn't have written x1. Sorry about that. We know that G1 transpose x is bigger than or equal to G1 transpose y for all y. And also G2 transpose x is bigger than or equal to G2 transpose y for all y. Right, we know that those properties are true because I told you that G1 and G2 were both in the normal cone. And T1 and T2 are non-negative, right? So therefore, I know that this is bigger than or equal to T1 G1 transpose y plus T2 G2 transpose y for all y. Right, from these two properties above, and the fact that it's very important that these two be non-negative. If I allow T to be negative, then this would be the wrong, one of these would be switched in terms of the inequality. And of course, that's just the same as this, just going back to the the linearity of inner products. Okay, so we've just shown that actually for all y, the inner product of this vector with x is bigger than or equal to the inner product of that vector with y, and that means by definition that this thing's in the normal cone. Okay, so all of the examples that I didn't prove convexity or the things for cones, they're very much like this one, just a matter of checking the definition.
Normal cone, can it be empty?
Good question. Let's answer that using just the definition of cones. So I told you it's always a convex cone. So cones always contain what point? Cones must always contain 0. So that means it can't be empty. Okay, the normal cone can't be empty because it'll always contain 0.
But it's possible that it only contains 0.
Right. So what's an example of an...
if the set C is not convex.
Yeah, but even in this example, for what points is a normal cone only going to contain 0?
Any point inside the set?
Right, any point in the interior. So for example, this point, right, the only vector that's going to have maximal inner product with this point is going to be 0. Right, because for example, these vectors should have bigger inner product with any vector than that one or something like that. Okay? Good question. So I've been drawing the normal cones on the boundary because they're more interesting that way. Okay, the PSD cone, positive semi-definite cone. This is another very important one. It turns out that if you think about the set of all matrices that are symmetric, this is my notation for a symmetric n by n matrix. Set of all matrices that are symmetric and that are positive semi-definite, which means that actually all of their eigenvalues are non-negative. That's one definition of positive semi-definiteness. That forms a convex cone. Okay, so we note that by this same Sn but with a plus. It's a set of all symmetric, positive, definite n by n matrices. So okay, just a quick refresher in case people have forgotten. So this means that, and here I'm thinking about X as a symmetric n by n matrix. This means that all eigenvalues of X are bigger than or equal to 0. Another definition, I can say maybe i.e. Another definition is that A transpose X times A is bigger than or equal to 0 for all A, for all vectors A. Okay, those are two equivalent conditions. for positive semi-definiteness. So make sure you're comfortable with, the eigendecomposition of a matrix, what it means things to be an eigenvalue, positive semi-definiteness. If that stuff's rusty, make sure to brush up on it because we're going to be using this very fluidly from now on. And this is my notation for something being positive semi-definite. This curly bigger than or equal to sign. Okay. So it turns out this thing is a convex cone over matrices. So let's check that also. So what happens if I give you x and I give you y that are in this set of positive semi-definite symmetric n by n matrices? So now I want to check that, let's say, t1x plus t2y is also positive semi-definite for all t1, t2 bigger than or equal to 0. Okay, this one may be a bit harder to check. I mean, it requires you to know a little bit more about eigenvalues and eigenvectors, but this one's easy to check, this condition. These are equivalent conditions for positive semi-definiteness. So we have to check that this thing is positive semi-definite, this matrix. So let's just do it like this. Take any vector A and do A transpose this matrix times A. Okay, that's the same as T1 times A transpose X times A plus T2 times A transpose Y times A. Okay, by positive semi-definiteness, each of these is bigger than or equal to 0, so this whole thing is bigger than or equal to 0. That's true for all A. Okay, so therefore, this thing is PSD. So this is a convex cone. So here's something you could do in your spare time if you like this kind of stuff. Open up MATLAB or R or whatever your favorite programming language is, and plot the set of matrices that are, say, 2 by 2 matrices. Okay, because symmetric matrices that are 2 by 2 really only have 3 elements. So you can actually plot in a 3D plot the set of PSD matrices that are 2 by 2. It's a very funky shape. You'll kind of see why.
Is there a positive definite cone as well? I mean, instead of positive semi-definite, we take positive definite.
Well, by our definition, no, right? Because 0 has to be in every cone. But it is the case. You can check whether I'm wrong or not, but I would be pretty sure that the set of positive definite matrices is the interior of the PSD cone. Good questions. Okay, let's go through some key properties of convex sets. So I gave you a bunch of examples. So this is the way it's going to work. I'm going to give you a bunch of examples. I'm going to give you a bunch of key properties of convex sets. And then I'm going to give you a bunch of operations that preserve convexity. It means things that you can do to convex sets and retain a convex set at the end. So if in the future I give you a convex set, it's some very messy looking thing, rarely will you go and check the definition of convexity. That's usually the most work. What's usually easier is to think, oh, I remembered that I learned this is convex and this is convex. And what I'm seeing now is some combination of these two. There's some function being applied that's combining these two. And I know that actually that's an operation that preserves convexity, so this thing I'm looking at must be convex. That's the usual workflow for checking that sets, or even more importantly, functions are convex. Okay, it's the same workflow. I'm going to give you a bunch of examples of convex functions, and then a bunch of operations that preserve convexity. And key properties as well, because this is why we like convex sets and functions, because they have properties like this. So here's one of the really important key properties of convex sets, the separating hyperplane theorem. The theorem is as follows. If I give you any two convex sets that are disjoint, which means they don't have an intersection, then there's a hyperplane that separates them. Okay, and on your homework, you're going to look at variants of this, which are like strict separation and other things to have you work with this. But yeah, it's a very important property of convex sets. So formally, it means that I can find a vector A and a real number B such that A transpose X is bigger than or equal to B basically for all X that are in D, and A transpose X is less than or equal to B for all X that are in C. So they lie on either side of that hyperplane. That's where the name separating hyperplane theorem comes from. Okay, all we require is that C and D be convex and they don't have an intersection right here. So here's just a tiny bit of a brain teaser. What if I tell you that C and D are convex and I want strict separation, which means that I want to find an A and a B such that A transpose X is strictly bigger than B and A transpose X is strictly less than B. Is that always possible? I'm telling you that A and B don't intersect. So if you don't think it's possible, then yell out a counterexample. So I have two convex sets. I want to have a hyperplane that strictly separates them. Okay, how about, what if I allowed the sets to be open? Yeah.
You have a closed hyperplane on one side and open one on the other. Or a closed half space.
Yeah, sure, that's a good example. So here are my convex sets. So C is a set of all X such that A transpose X, I guess you can't see that, is less than or equal to B. And D is the set of all X such that A transpose X is strictly bigger than B. Okay, so there is no single, so in other words, C is everything including this boundary, and D is everything except the boundary, okay, on this side. So I can't find another vector called C and, or I guess I should call it maybe A tilde and B tilde. So we can't find A tilde and B tilde such that, you know, A tilde transpose X is strictly less than B tilde on C, and A transpose X, or A tilde transpose X is strictly bigger than B tilde on D. Right? You can just see pictorially that I definitely cannot find something that strictly separates those two. So that's a good example. That's where one of the sets was open. This may be a surprise to you, but even if C and D were both closed, still not possible. Okay, so here D is open. Even if C and D were both closed, still not possible to find strictly separating hyperplane. And convex. We're going to keep convexity. Anybody have an example for that? Both closed. Okay, I'll let you guys keep thinking. Somebody post a question on Piazza if you haven't figured it out, and I'll share the counterexample. There's probably many. But you'll do some thinking kind of somewhat like this for your first homework. Okay, supporting hyperplane theorem. This one's also very important. This says that if I have a convex set, and you give me a boundary point of the convex set, then I have a hyperplane that supports it, which means that I can find, say, an A and a B, such that at this point I get A transpose, suppose this point is called x naught. A transpose x naught is equal to B, and I get, let's say, A transpose x is less than or equal to B for everything on the set. But on the other side, I get A transpose x is strictly bigger than B, okay, or bigger than or equal to B. That's called a supporting hyperplane. In other words, I can write it like this. I've gotten rid of the B in the notation just with the property that A transpose x is less than or equal to A transpose x0 for all x in the set. And x0 is that boundary point. So that's a very important theorem. We typically don't use convex sets that much going forward from here on. But we use convex functions a ton. And it turns out that the way we prove things for convex functions when it comes down to it, probably not the way you see it in class, but the way that really a lot of the properties that we know of convex functions are proved, it comes from convex sets. So for example, the existence of subgradients. We're going to talk about convex functions and a notion of a gradient for a convex function that's not smooth. Subgradients. The existence of subgradients comes from this, the supporting hyperplane theorem. So you might ask me, why do subgradients always exist for a convex function? That's the answer. Turns out it comes down to this notion for convex sets. Both of these theorems have partial converses. You can look at section 2.5 of the Boyd and Vandenberg book in case you're curious for converses of these theorems. Okay, I took way longer than I had intended to on convex sets, which is always what happens. I'll just tell you what the operations are that preserve convexity real quick, and then we'll take a break and we'll come back and do convex functions. So the intersection of any two convex sets is convex. If I take a convex set and I scale it and or translate it, which means I multiply the set by a number a and I add a vector b to it. So by ac plus b, I mean the set of all ax plus b where x is in the set C. That's called, this is a scaling. This is called a translation of the set. That's still convex when C is convex. This one's really important, and you'll explore something like this on your homework. If I take any affine image of a convex set, it's convex. Now if I take any affine preimage of a convex set, it's convex. So this is notation that's important to be familiar with because we'll use it a number of times throughout the semester. So let's suppose that f of x is the following function. It goes from Rn to, let's say, Rm, because A is a matrix. Suppose A is an m by n matrix. Okay, then when I pass in a vector x, f of x gives me back ax plus b. It's called an affine function. The affine image of a set, or just the image of a set under a function f, is the set of all f of x such that x is in the set. That's what we mean by the image. I just apply my function to every point in the set. And when f is affine, it's just called an affine image. Okay? If C is convex and f is this affine function, that's a convex set. So that means I can take any affine transformation of a convex set and obtain convexity. Very useful fact. This one's also very useful. This one's maybe a little bit less intuitive. If I have a convex set and I apply, if I look at its affine preimage, then that's also convex. So this is notation that I think some people get confused by, because I'm going to use this notation not to mean that this is the inverse of my function. So this function may not have an inverse. It could be the case that A goes from, let's say, R100, so f goes from R100 to R10. It's not going to be invertible, right? Suppose f drops you down a lot of dimensions. So f inverse may not exist, but this still makes sense, what I'm writing. This is just a set of all x for which, if I had applied f to x, it's in the set D. Okay, it's called the affine preimage. If f inverse existed, if this function had an inverse, then this would actually just be the image of D under f inverse, but that doesn't need to be, f inverse need not exist in order for me to write this down. Okay, so it's the set of all x for which when I apply the function to that point x, it's in the set D. This is also convex, provided that f is affine and D is convex. I think it's much more surprising that that's true. So let's look at an example of how we use these properties. This is something called a linear matrix inequality. If you are interested in SDP programming or SDPs, and or you'll be forced to be interested in SDPs because we'll cover them in this course, then you'll see inequalities of this form. So this is inequality in a variable x, given matrices A1 through AK and in a matrix B. And all I'm going to tell you is that these matrices are symmetric. Okay, they don't need to be positive. There's symmetric matrices A1 through AK and a symmetric matrix B. And I'm saying let's look at all this points x for which if I take x1 times the whole matrix A1 plus x2 times the whole matrix A2 all the way through xk into matrix AK, that thing is curly less than or equal to B. What that means is that if I take B and I subtract this matrix from it, that thing is positive semi-definite. Okay, that's what that means. So this means that B minus this thing is positive semi-definite. Okay, we can define an ordering on symmetric matrices using this notion, right? Just in general, if x and y are symmetric matrices, I can write that to mean that y minus x is positive semi-definite. Okay. This is called a linear matrix inequality. It's a generalization of like a linear inequality. So I'm asking for the set of all k vectors x for which this is true. So the set of all x for which the sum of xi, ai, I going from 1 to k is less than or equal to b. Turns out this thing is convex. An interesting property is that it's convex no matter whether a or whether ai and bi were positive semi-definite. Okay, it's always convex. So there's two ways to prove that, probably more. The first way is to check the definition. Okay, we've done that before for different examples. I'm not going to do that this time. You can go ahead and check that if you want to see kind of both routes on your own. Let's look at the second way of doing it. The second way to doing it uses the combination of the fact that we know that the PSD cone is convex, and we know that affine preimages preserve convexity. We just put those two together and we declare that this thing must be convex. So stepping through that a little more carefully, let's think about a function that goes from Rk to this set of symmetric n by n matrices, which is this function. You pass vector x, it gives you back b minus the sum of xi ai. Okay, that function is actually affine. Think about how it acts on the variables x. It's just this is just adding constants, and this is just linear. So it's just an affine function. And if I'm thinking about this set is equal to the set of all x such that this is true. The set of all x for which, when I apply this affine to x, I get a positive semi-definite matrix back. That is directly from the way we constructed F. Which means that this set is actually just the preimage of the PSD cone with respect to this affine function. That's convex. We already checked that. You can remember that from now on out. That's an affine preimage. Therefore, this is convex. Okay? As simple as just putting together those two pieces. And that's more along the lines of the kind of things you'll be doing from now on out to prove convexity. Okay, let's take a break. I've talked about convex sets for too long. When we come back, we'll talk about convex functions. Just a few minutes break. Let's jump back into it. I'm gonna skip covering this thing called the Fantope. I think it's really neat, but we're going to talk about it in 2 lectures or something. So we'll come back to it then. It's basically like a polyhedron, but for matrices. Okay, so we'll get back to it then. You can. It wouldn't hurt to look through this slide just so that what I say later is less confusing, but we'll cover it in a few lectures. And more operations that preserve convexity for sets. We almost never use this stuff. I hate to be so bleak, but I personally don't use this very much, but it's just worth saying. Perspective images and preimages are both convexity preserving operations. So are something called linear fractional images and preimages. I'm not going to cover them in great detail now because we don't have that much time. And plus, like I said, I don't think we actually use them all that much. But these are a bunch more things you can do to convex sets to retain convexity. And there's an example here in the slides of how you might use them to prove convexity for a particular set. Okay, so let's go on to convex functions just in the interest of time. Remind you that's the definition. The domain must be convex. You must have the function lying below the line segment, the graph of the function lying below the line segment. That's the definition of convexity for a function. I already went through that. And a concave function is just one that has the opposite inequality being true. So f of the quantity tx plus y minus ty must be bigger than or equal to instead of less than or equal to. For concave, it's bigger than or equal to t times f of x plus 1 minus t times f of y. Another way of thinking about it is that f is concave if and only if minus f is convex. So, think about the negative of the function being convex. That's how we can think of a concave function. So with this relationship in mind, essentially everything I say about convexity for functions also has an analogous definition for concave functions. Just apply, just think about minus f instead of f, okay, to get all of those details straight. So here are 2 very important modifiers. strict convexity and strong convexity. So a function is convex if the previous definition held. A function is strictly convex if we get strict inequality instead of just less than or equal to. We get strict inequality whenever t is strictly between 0 and 1. That means the function must lie strictly below the line segment, not just less than or equal to the line segment, when t goes between 0 and 1, not including 0 and 1. Okay, so another way of thinking about it is that f is convex and it has more curvature than a linear function. That's the way I think about strict convexity in my mind. It has to be curved in some way. Can't just be like a linear function. How about strong convexity? Strong convexity comes associated with a parameter. This is just a number m, which is positive. So we say that f is strongly convex with parameter m, or sometimes we abbreviate it by saying f is m strongly convex. If this holds, if I subtract off m over 2 times the 2 norm of x squared from my function f, that's still convex. Okay, so strongly convex f means that g is convex where g of x is equal to f of x minus m over 2 times the 2 norm of x squared. That's our definition for f being m strongly convex. So thinking about it again in terms of curvature, f is convex and it's at least as curved as a quadratic function. It can't just be more curved than a linear function. It needs to be kind of at least as curved as a quadratic function, and it's in particular this quadratic function. So even after we take away that quadratic function, the residual is still convex, f minus m over 2 times the norm of x squared. And if you look at these definitions carefully, you'll see that strong convexity implies strict convexity implies convexity. Okay, so that's the strongest property. So if a function is strongly convex, it's definitely convex, it's just more. Okay? And analogous definition for concave functions, just apply everything to minus f, basically. Okay, yeah, question. Good question. So strictly convex function that's not strongly convex. How about I bounce that back to you guys? Yeah, sure, that's good. I mean, we need to know the domain, but yeah, that's a good example. So let's think about 1 over x on 1 to infinity. Well, my drawing's not great, but you get the point, right? So I cannot find something like a quadratic under approximator to that, but it is strictly convex. Good question. Other questions?
So is strong convexity defined as if there's any m that satisfies it?
No. So strong convexity is defined for a particular m.
So it can be strong convex for some small m or some large m, but not for some larger m. If like it lies between two quadratic functions.
Yeah, so I didn't quite understand the question, but strongly convex means that if you tell me that, for example, f is 1 strongly convex, that means that when I subtract off the 1/2 times the norm of x squared, that function is still convex. And maybe jumping a bit ahead, we'll see that there are functions that are sandwiched in between two quadratics. Those are functions that are strongly convex and they have another property which we call a Lipschitz gradient. That shouldn't mean anything now, but that's going to be an important condition when we start talking about gradient descent, for example. And on your homework, you're going to derive a bunch of equivalent conditions for strong convexity and for what it means for a function of a Lipschitz gradient. So there are a bunch of equivalent ways to express strong convexity if f is smooth. Okay, so you're going to explore those on your homework. They'll be helpful for the rest of the semester too. Yeah?
There's no separating height of plane between this and the point about 1 over x?
Is between what and what? Sorry?
X less than 0 and x on the other side.
There you go. I think you just You got it, which is, here's an example of two convex sets that are closed that have no strictly separating hyperplane. So that answers our trivia question before. So if I define, say, C to be the x-axis and everything below, maybe I'll just truncate at 1 for simplicity. So that's C. And D is 1 over x and everything above. Then those two things are closed convex sets. There's no strictly separating hyperplane, even though they're both closed. I didn't even plan that. That was good. Where'd it go? OK, so some quick examples of convex functions. A bunch of functions that you know that you can draw that are univariate are convex. For example, the exponential function is convex. E to the ax is convex for any a. The power function is convex. X to the a is convex when a is bigger than 1, or when a is less than or equal to 0 over r plus just the positive reals. So if I think about if I define the domain of this function to be just the positive reals, then that's a convex function. You can just draw yourself pictures, to ensure that's true. This function x to the a is concave over r plus when a is between 0 and 1. Okay, so think of like the square root of x, that's a concave function. And log is concave over r plus plus. So this is my notation for saying the strictly positive reals. So I guess, yeah, I don't know if I've been sticking to consistent nomenclature. Maybe you can call this the non-negative reals and this the positive reals. But log is not defined at 0, so that's why this is its domain. Okay, so here are just some examples. Affine functions, the only functions that are both convex and concave. Okay, so they're pretty special functions. They satisfy an equality here. Okay, they have an equality here. So they're both convex and concave. Quadratic functions are functions of this type, 1/2 q, x transpose qx plus bx plus c, where q is a matrix. That's convex provided that q is positive semi-definite. So, okay, let's hold off on why that is in for just a second. And a special case of a quadratic function for those of us who like regression is the least squares law. So think about the variable here as being x. This is actually always convex because if I expand this, y minus ax transpose itself. So that's one way of thinking about the 2 norm. It's a vector transpose itself. If I expand this, I get a quadratic. But q for this quadratic is a transpose a. Okay, and a transpose a is always positive semi-definite. If I take a matrix transpose itself, it's always PSD. Make sure that that makes sense to you, given the definition for positive semi-definiteness. Those are some examples. A norm is convex. Any norm is convex. Follows right from the definition. And we'll be looking a lot at LP norms in this class, which are defined like this. So for p bigger than or equal to 1, we define the LP norm like this. So this is the usual definition for the norm. It's the sum of the absolute values, which you probably have seen before. And for the infinity norm, it's just the max absolute value of the components. That's the way we define it. Also, though, a little bit later on, there'll be some important norms over matrices that we'll use. The two that we'll pay a lot of attention to are the trace norm and the operator norm. But I'm just going to kind of quickly skip those, pass by them real quickly now, because we won't be too concerned with them for at least a little bit. Other convex functions, the indicator of a convex set is convex. So if you give me a set C, I can define its indicator, which is 0 when x is in the set and infinity when x is not. That's convex when C is a convex set. The support function is convex no matter if the set is convex or not. So this is kind of an important, it's very important in relation to the indicator function. I denote it by I star of C. That'll become clear later why we use this notation. And this, I'll let you check that that's convex based on the definition. That's convex no matter if C is convex or not. It's the maximum inner product I can make with x over all vectors in a set C. Max itself is convex, so if I take the max of like the components of x, that's a convex function, yeah.
Thinking of the indicator function as convex is kind of weird because, I mean, it looks a little like that, right? And then if you were to join points here and here, then you have this section line, this section line, this curve. I mean, it's
Do-
quite non-intuitive to me why it's convex.
Check the definition. Go back to the definition. I think you'll see that it's key is the domain. Go back to the definition and look at the domain of that function, right? So then you'll see that the domain is in fact C and has that property for all points in the set C. Okay, kind of getting towards the end of time. Key properties of convex functions. So this is the connection between convex functions and convex sets. We can define for any function in its epigraph. That's the set of all points x comma t such that f of x is less than or equal to t. Okay, so let me, in fact, what we had before, let's just think about the function 1 over x. 1 over x. This is its epigraph. Suppose its domain was just 1 to infinity. That's its epigraph. Okay, it's all points on the graph that lie on the graph of the function and above. That's the epigraph. And it turns out that we can define that for any function f by this definition. And that's a convex set if and only if f was a convex function. So that's the connection between the two. And in fact, pretty much everything that I've told you about convex sets so far, or convex functions so far, and that I will tell you about convex functions, can be proven from what we know about convex sets using this relationship. Okay, so it's really a close connection between the two. If f is convex, then its sublevel sets are convex. That's actually not, the converse is not true. So I'll let you think about that one as well. I'm going to keep moving on because we push up against the end of time. Here are very, very important properties. Okay, this is ones I want to stress. If f is differentiable, if it has two derivatives, then we have sufficient conditions for convexity, and in case of we have necessary and sufficient conditions for convexity. Okay, so if f has a derivative, then it's convex if and only if, well, of course, its domain must be convex, but also this property is true. F of y is bigger than or equal to f of x plus the gradient of f of x transpose y minus x. So this says that the function lies above its tangent line. So here's a function f. Here's a point x. Here is the equation. Here is its tangent line. Okay, and I can think of this as f of x plus, in one dimension, f prime of x times y minus x. That's the equation for this line as I let y vary. And f is convex if and only if the function lies above its tangent line. So f of y is bigger than or equal to this thing for all y. This is just the multivariable version of that. Okay, another way of thinking about convexity. Very important property. I think probably even more useful in some sense because you can use it to check convexity quite easily is a second order characterization, which is that if f has two derivatives, then it's convex if and only if, well, of course, this always has to be there, but it's Hessian. It's Hessian, and if you've forgotten what that means, make sure you take a look at that. This is just the matrix of its second derivatives is a positive semi-definite matrix for all x. So in one dimension, that just means that f double prime of x is bigger than or equal to 0 for all x. Okay, the function must be curved upwards. Something you probably remember from, calculus at some level whenever you took that. Okay, this is the multivariable version of that. The Hessian matrix must be positive semi-definite. Okay, just to quick refresher. This is a matrix. Its ith, jth element you get by differentiating with respect to xi and then xj, or the other way around. Okay, so this is a matrix. These are its elements. That matrix must be positive semi-definite. It's equivalent to convexity. Okay. Let's see. I think probably the most important thing to do is to go through the operations that preserve convexity, and then on Monday I'll probably come back and just give a bit more details on some of these, but let's go through at least these. So if I have any convex functions f1 through fm, and I take a non-negative combination of them, so a1 f1 plus am all the way through am fm, provided that these are non-negative, that's still a convex function. Okay, it's a helpful property. Here are our two very useful properties that I think are a bit surprising. I can take the pointwise maximum of convex functions, and still retain convexity. So let's suppose I index some functions by s, and I have a bunch of functions fs of x, and each of those is itself convex in x. If I take the max of all these functions over all s in some set capital S, then that's always a convex function at the end of the day. It doesn't matter what this index is or how big this index set is here. It could be infinite, could be uncountable. It doesn't matter. It's always true that I can take a pointwise maximum of convex functions and retain convexity. Okay, so it's a very useful property. This one is it's about minimization rather than maximization, and it requires a bit more conditions for this to be true. If I have a function that's jointly convex, say in two parts, x and y, so it just means it's convex in its argument. So call this z, it's convex in x, y. And C is a convex set, then I can minimize partially. Let's suppose I minimize y over C to get a function out that's only a function of x. That's still a convex function. C is convex. So the difference here is that we had no restrictions on S. We didn't care at all what S was, which is why I wrote these notationally a bit different. Here we require that, first of all, G be convex in both of its arguments, and also that the set over which we're minimizing be convex. Okay, so that's called partial minimization. Let's just see the implications of that, and then we'll quit. And next time, we only have maybe like one or two more properties that I wanted to get through. So here's the application of that. Let's suppose that you give me an arbitrary set, and I'm going to define two functions. The first function is the maximum distance to any point in the set under an arbitrary norm. So pick your favorite norm. The L2 norm, the L1 norm, the L3 norm, if for whatever reason you like that. And look at the maximum over all points in the set C of x minus y, the norm of x minus y. Let's define that to be our function f. So I claim that actually f is a convex function. Why is that the case? It's because for any fixed y, this function, the norm of x minus y, is convex. Because it's just, well, I guess do we get to the affine composition rule? I mean, that's not too hard to check that it's convex on its own. The norm of x minus y is convex. I already told you the norm of x was convex. This is just changing the offset. Okay, so by the pointwise maximization rule, f is convex. So if I have some very weird set, okay, very non-convex set, and I define f to be the function that gives me back the farthest distance, that's always convex. Okay, that's kind of a surprising fact, I think. Now, let's suppose this set was convex, and let's consider the minimum distance. So this is the distance between x and its projection onto C. That's only convex if we assume that C is convex. Otherwise, we can't say anything about it. Okay, essentially the same logic will follow. We just use the partial minimization rule. But if I want to look at the closest point, okay, so instead of the farthest point, if I look at the closest point to a set, it actually matters whether the original set in question was convex. Okay, so just difference in how those two, and the implications of those two rules. Okay, so I guess I'm over time by a little bit. I'm going to quit here. Remember to do your quiz, and we'll see you guys on Monday.